Hello. This video is the second in a series on DNA and information and why random processes cannot create functional information. What we'll do in this video: we'll walk you through computer programs that modify character sequences. The code will modify our DNA, modeling evolution. We'll do scientific experiments to confirm or deny the hypothesis that random processes can generate functional information. In this set of programs, we will actually represent DNA as Java code. This allows us to attempt to compile the code, measuring whether or not the organism lives. Now, if you haven't seen the first video, you probably want to stop and take a look at that one first. I'll have it linked here in the description. Now, as we do these experiments, we have to remember what the basic requirements of common descent is, because that's the hypothesis that we're studying. The hypothesis is that natural processes must be able to modify DNA, because that's how changes occur from the parent to the child according to the idea of evolution. They must be able to create new functional information, but even more, they must create superior functional information, otherwise the organism never progresses. Scientifically, we'll see that this is just not possible, because natural processes cannot even create functional information. So, let's get started. You may recall from the previous video that we compiled our Java programs, and here we have Java-C, followed by the name of the file reproduceJava.java, and I'm going to press return here, and that compiles that program. So in this video, what we're going to do, this reproduceJava.java file, is a program that can actually compile other programs. And in that way, it's very much like DNA, because DNA actually gives the information about biological machines that process DNA. Now, let's bring up the program reproduceJava.java, and we are going to go through this. It's fairly similar to the previous one, but it builds on it. Like we talk about, evolution says that it can do this, which is take something simpler and make it better. But I'm going to walk through this because it is a little bit more complex. So first, let's talk about the basics of what's happening. You'll see that we've got some of the lines that are similar, but if you remember, there was this section called main that kind of did the work of the program. Now we're going to add some other sections of code. These are called functions, and these actually, it turns out, are fairly equivalent to what genes are in the DNA. But they are simply functional units of code. So for example, we will start the evolutionary process. We have another section of code here that's going to create the DNA. It will take DNA from the parent and create the DNA from the child, very similar to what we did on the first videos. Then we will go through the process of being born, and what this will do, this is actually the code that actually tries to compile our child program, the cell.java. We'll explain about that. And so this is the thing that actually tests whether or not the organism lives. And then, of course, in real life, the child will grow up, and then it can become a parent. So that's what this growUp is. And the showResults is to show the results of this going on. Okay, so let's start back at the top of the program and walk through this particular program. So just if you want to follow along and do the exercises yourself, because that's really the nature of this set of videos, is so that you can actually do the experiments yourself. So all you need to do is stop the video at the appropriate place and type it in and give it a go. So at the top, just like the previous programs, we have the import Java IO and the random, so we can create random numbers. Now the name of this file is reproduceJava.java. That's the name of the file, so the class has to be named the same without the extension. We'll have a parent DNA and the child DNA and the valid characters that we can represent, the in file and out file. We've got a new variable here called process P, and that's what we'll use to actually do some of the processing. We'll get to that later. We also have generations, because what we're going to do is not just stop with one attempt at reproduction, but we will see whether or not, if that child lives, then we can go on to the next generation. And what we're going to try to do is we're going to try to see if we can get 20 generations. Can we go 20 generations without dying? And that actually isn't even measuring whether things are getting better. That's just, can we even survive? And we already know in biological systems, all of us have mutations that are detrimental to us. And those are diseases of all different kinds and deformities. Those are things that we don't like, but we can survive. So we know that mutations can occur, and they make things worse. What evolution claims is it makes things better. So we're going to try to get to 20 generations and see if that the end resulting children are better than the parents, more functional. So the first function or method is the main method. So that's really the area that runs things and controls everything as a whole. So the first thing that we're going to do is startEvolution. So let's jump down and look at that for a second. This reproduceJava is just some syntax. You'll have to look at what static methods are in Java if you want to understand that more. But basically it's just going to come down here to this function. So in computer programs you can start at one place. It's not like reading in English where you just go sequentially down. You can jump around from one place to another. So what this says is come down to this function startEvolution. And what's going to happen here is, I'll skip this part, just look here, we will have a parent cell, and we're going to delete that parent cell because this is just a programming thing. We don't want to accidentally make a problem because the file already exists. But all we're going to do in this particular function is we're going to take an original cell and turn it into the parent cell. So we're starting the process as if we're even giving evolution the idea that a cell came into being. And so we had some living organism to start with. We're totally avoiding the question of how did that original cell get started? How did the whole machine of evolution get started? How did DNA come into existence? How did the processing of DNA come into existence? And all of those kinds of things. So we assume that there was an original cell, and so that becomes our parent cell. So this just starts up the program cleanly. So like I said, I'm not going to get into too much detail about this, but this runtime command basically allows you to execute commands on your operating system. This is running on Windows, and so we're going to execute out to the Windows shell and execute a command to delete the parent cell. And then we're going to wait for that to end, and when that's done, then we'll execute another command to copy the originalCell.java to the parent cell. So we hop over to the originalCell.java. That one's already in existence, and it's just a very, very small Java program, and it's going to it has that main section. It's all in a single line, and it's going to all it's going to do is print out a statement that says I'm a cell. And so that's about as small as you can get with a Java program. Now you may see this this little squiggly underline red here, and that actually means that if you tried to run this program or compile this program, it wouldn't work. But the reason is we're trying to give evolution as much help as possible. The syntax of Java is that the name of the class must be the same as the name of the file, and so that's what that little red line is complaining about. But what we are going to do is we're going to create the parent, and then we want to derive from the parent to create the child, and we don't want to create the function to be able to read this and understand it and change the name according to the what the file name is. We're trying to make it simple, so if you don't have a lot of computer experience, you you don't have to understand that. So we're going to try to create the child named Cell. So that's what's going on here. So we come back to the reproduce Java. We've talked about startEvolution, and that's what I was saying. We take that original cell and it becomes the parent to start the whole process. And we can come up here. After we started the process, what we're going to do is this reproductive state of creating the DNA from the parent to create the child, and then we're going to try to be born. Now, when this being born function runs, it has a result to tell you whether or not the compiling succeeded or failed. That has a thing that's called an exit value, and this exit value, if it's equal to 0, then we've succeeded. If it's equal to something other than 0, then it has failed. So, in this particular case, what we're going to do is we're going to, if we have been born alive and we actually have a living child, then we will increase the generations. So we're counting how many generations that we have surviving children. Then we will grow up, and we will continue the process to see how many generations we can do. We'll continue to do this as long as, again, the exit value is 0. So as long as we have a living child, and as long as the generations are less than the total maximum number of generations, which is 20, which we're trying to achieve. This symbol right here, these two symbols here together, have the idea of and. So it has to be, this has to be true, and the other one has to be true. And then finally, after we've tried to create as many generations as possible, we'll show the results. And the results are either going to be that the child has lived and we've made it a certain number of generations, or the child has died. So we'll see those in more detail. So let's look at the createDNA function. That is very similar to what we saw in the other videos, where you basically are reading from a file. In this case, instead of it being parent.html, or reading from a parentCell.java, and remember in the evolution, the first step, startEvolution, it created this parent cell from the original cell. So it will take that parent cell and it will output to a cell.java. This would be a child cell. So we're going to create the child here. And again, we just read in the line from the input file, the parent, and we will create that forms the parent DNA. Then we will do what we had done before, which is we will randomly mutate, do a point mutation somewhere along that stream. So here we have the random number generator. We calculate the location. Again, look back at the previous video to understand what's going on here. But if you just want to follow along, all you have to do is type it in and it will run. Then we have to determine what kind of mutation we'll take, go back to all the possible characters and choose one of them at random, and that will be the mutation. And then we will substitute into the parent string, the parent DNA, that mutation to create the newly formed child DNA as a result of mutating the parent. Then we will close everything and we'll write out the child DNA so it has been written out to cell.java. And so that is what the step of creating the DNA is. Now we go back up here to the main thing, and you can see we create the DNA, and the very next thing we do is we're born. We try to be born. So we're going to be born here, and all we're going to do there is we're going to try to execute that Java cell. To actually compile it is actually what we're doing. We're going to execute a command to compile the child, the cell.java, and we're going to wait for the result. And notice here this P, that's the process result, is going to either have an exit value of 0 if it's successful, or something else if it fails. Now, if the child actually is a valid, viable child, if that child is able to live by compiling, then we'll let it grow up. And really what we're doing here is we're just going to, again, get rid of that an existing parent cell to avoid any computer errors in copying the files or renaming the files. And we're just going to rename the child to a parent. So the child is growing up. It's becoming a parent cell. And so that's all the growUp is really doing. And as we come back to the top here, after we've grown up, then we repeat the process because the child has become the parent, and so it will try to have a child. And so that's what's going to happen there. Now let's go down to the show results and look at that just a little bit more to see what it is. Okay, again, you can write out this code, copy out this code, and pay very close attention to all the little braces that we have here. You should have 105 lines if you do the spacing exactly as I did. And so I'll just run through this. Let me go ahead and run through this very quickly so that you can see it. So there's you can stop it if you want to see lines 1 through 31. Okay, and I come down here. We'll pick up and overlap a little bit here, so we'll start lines 29 through 55 going through the createDNA, so stop it if you want to copy that. And then the sections about being born and growing up. And then finally the very last function all the way down to the end of the file here is show results. Again, just stop as you need. So what's going to come here? We've already seen this kind of idea of this runtime, which is allows me to execute these commands. So what we're going to do is we're at the end, when we're done with everything, we're going to test to see how many generations have occurred. And this equal sign tests to see if the number of generations, as we've counted up, is equal to the maximum number of generations. In other words, were we able to achieve 20 generations? If we have, then we've made it. So we made it 20, the maximum number of generations. So this is a variable, so you could change how many generations you test. But we've made it this maximum number of generations, and are now, so what it's going to do is going to print out the result of what we saw here. And this little \n just gives you a new line so that you can see space between this sentence when it outputs and the rest of the code. So what it's going to do here, this is just a command to type out the cell.java, and that means it's going to just show you or print to the screen the different the lines in that file, and we'll wait for the end of it. This set of instructions here is just going to read from the input stream of the process. So because we're executing through this process, you don't read it from a file, you're reading it from the process itself, and that's the way you do that here. And so you will have a line, and we will read each line and continue to read each line and print out each line, read and print, read and read and print, until we have no more lines left. That's what not equal to null. That's what this means, is there's no more lines left. And then we will close the input file. So that just outputs the results. So that's if the generations are equal to the maximum generations. In other words, we've reached all of the generations. Otherwise, or else, we didn't make it. We did not make it all the way to 20 generations. So in that case, we tell you exactly how many generations we did make. We made it however many generations, and then we died out. So we didn't make it all the way to 20. And it follows exactly the same kind of behavior, which is here we just take the lines, we read in the lines. This time we're getting an error stream because, again, the test was, did we make it to the maximum number of generations? If we didn't, then there was an error that happened. And so that's what this is. So we're going to get the error stream and just output that. So it's very similar to this one, just a slight bit different. Okay, so now that we've seen what the program looks like, let's actually compile it. So Java C, reproduceJava.java. So now that's how we compile this particular program. Hit return, and it's all successful because I already know that that code works properly. Now we will run it. So we are going to now, as we type in Java, no C, we get rid of the extension. That means that we're going to actually execute the reproduceJava program. So that is going to simulate evolution and see how many generations we get to. So we died in the first generation. In other words, the child did not live. And so you see the results of the error. So there was, it tried to create this CXASS instead of class, and that's not valid Java, so it didn't work. So let's try again. Didn't make it. It died again within the first generation. Okay, so let's stop for just a second and think about what we're seeing and what this means. Remember, our hypothesis is that we can apply mutations, natural processes, unguided, undirected, unintelligent changes to a DNA string, and the end result would be a better child, because that's what common descent requires. And so what we're doing is we're trying to model that, because this is information. DNA is just an information stream, and we can easily model that in computer systems. And so that's what we're doing, where we take that hypothesis, do an experiment, and see the result. Well, we've just done a couple of experiments here, and every single experiment that we've tried has shown not only did it not improve, but it actually got worse. And so the child died. And so each run is an experiment disproving evolution. Okay, so let's run it again. And it still didn't improve. What I was actually hoping is that it would make it this time at least one generation, because that is possible. There are places in which a mutation can occur and the child will survive. But let me point out one other thing, and that is here, if you recall, all we're doing is mutating one point. Only 1 point within the program, and we're still having all kinds of problems getting it to run. So here you can see, for example, it's showing us that this should be saying class space cell, but it put a random mutation in a place that a space has to be. Now, this is an extremely important point in discussions about evolution, because if you read books about from evolutionists that talk about how, oh, you can make small modifications and it will get better a little bit at a time, well, that's because what they're doing is they're thinking of this as a sentence. Now, as I look at this as an intelligent being who understands English and understands some programming, I can make sense of what this is supposed to be doing. And I can see, oh, there's just this little change here, and if I just get rid of this change, it will work. But the problem is, I'm applying my intelligence to this, and that's not what an evolutionary theory says. The evolutionary theory says that you've got undirected things going on and the machine's just behaving. And so DNA is actually processed in a mechanistic way. These biological machines just process it here. They don't understand. They don't. The individual machines are not intelligent in and of themselves. They are just processing the stream, just like a computer does. And so the computer doesn't know what is supposed to is supposed to be here. It has no idea what this information is about. It's just processing the information according to the rules that have already been set up by the computer system. So if you rewind the video and take a look at all the changes that we've seen, like for example here and here, each one of them was just a single mutation, and it killed the child. So it was very, very detrimental. So we're going to go through one more program in this video, but let's stop and think about mutations for just a little bit. All mutations are a combination of insertions and deletions, and that's it. Even a point mutation is an insertion and a deletion in the exact same point. Now, if our goal is a gain in functional information, it should be pretty obvious that deletions aren't really going to help us there. At the very best, they can just eliminate bad code. Just like the process of natural selection, all it can do is eliminate things. It doesn't create anything. However, to this point, we haven't actually done insertions into the string. So that's what we're going to look at now. So the program we're going to look at now is called reproduceJavaMulti, and that's because it can do both point mutations and insertion mutations. It could also do deletions, but as we've already discussed, that really doesn't increase the functional information. That should be pretty obvious. So let's take a look at the changes that we have between the other file and this file. They're essentially the same, but there's some modifications that we have. So I'm not going to do a line-by-line comparison of this file with the other file, but I am going to walk through this file and point out specifically the things that are unique to this one. So first, before we get started, let me make sure that if you want to, copy along, that you can just pause the video. So here we're looking at the introduction of the program and the main function. There is a startEvolution just like the other program, but it has changed because we're going to call this executeCommand. So we have another function that promotes reusability, and we'll talk about that a little bit more. Here we've got the createDNA, and we've introduced a new function called mutate, so that we can either mutate for an insertion or point mutation. So here's the function for the point mutation, and here's the one for the insertion mutation. And the insertion mutation is doing a mutation on the order of 100 to 300 characters. The reason is, if you look at these different functions here, that's about how big they are. So that's the reason for that size. And for the point mutation, in this case, we're going to randomly do a point mutation up to 10% of the DNA. We have the birth function and the growUp function. Again, they're reusing this execute command, and we just pass in the kind of command that we want to operate on. So again, that's the kind of thing that can be happening in DNA. That's the kind of thing that biologists have no real understanding of, because they don't really work in the information fields. And so they might call things junk DNA, or they think things that are very similar means they're the same. But you can see that most of these characters are the same, but these are actually doing quite different things based upon just a few differences in the strings that you see. The show results, we've minimized this a little bit, and the reason is because the more that you add the insertions, we actually have more mutations that cause problems, and so that can actually cause the program to hang a little bit. So we're not going to actually sit around and wait for the program to return if it's hanging. So instead, we're just going to try to compile, and then at the end display what the result is. So here's the execute command, and we pass in, this is a little bit different from what we've had before, and that is a command string. We'll come back to this to explain it a little bit more, but notice here that we're waiting for, and then we're going to destroy, so we'll talk a little bit more about that. And there's finally the display file, and that's the end of the program. Okay, so now let's go into a little bit more detail. You should have been able to stop wherever you want so that you can copy the code. We've talked about most of the things, but let's take a look at some of them. We've got the runtime up here now, and the random number generator. We've moved these up. So these kinds of functionality, these variables, are now global across all of the functions. And again, that's the kind of thing where you're reusing functionality. So this is pretty much the same as it was before. The evolutionary process is the same. The startEvolution is the same. It's just reusing some functionality. The createDNA is, again, essentially the same, except right here we want to call the mutate, whereas previously it was just doing an point mutation. So we just have the mutate. What it does is we generate another random number between 1 and either 0 or 1, which is two different values. That's what that means. And if it's greater than 0, it's either 0 or 1. So if it's a 1, it's going to do an insertion mutation. If it's a 0, it's going to do a point mutation. So about 50% of the time it'll do either one of those. So the point mutation is just the same type of code that we've had before, and especially if you look at the first video that we went over, the reproduce HTML multi, it does the same kind of thing. We're adding not just one mutation, but any number of mutations up to 10% of the DNA length. So here's the insertion function. So this is the most different part, the thing that we're adding and most interested in. So again, like I said, the number of mutations here that we will insert, the number of things that we're going to insert is going to vary between 1 and 300, actually 299, but that is roughly equivalent to a small function here in terms of the number of characters. Just like the point mutation, we find the mutation location, and then what we're going to do is we're going to break the string apart. And so we have an initial strand that is the first half of it, and the secondary strand, which is the second half of it. So we break it at this mutation location. And then what we're going to do is we're going to assign to the child DNA the first strand. And so that's what the child DNA starts as. And then this part right here, this little for loop here, is the thing that's actually doing the insertion of new information. And so what it's doing is just randomly getting characters from the set of valid characters, and that would be in the DNA world base pairs, equivalent to base pairs. And so it's just adding them and appending them onto this child. And then we call it an insertion because it's inserting before the secondary strand. So after we've done all of those additional mutations added on, then we add the secondary strand back on. And so we've inserted this mutational string in between the initial strand and the secondary strand. So that's what's happening in the insert. The beBorn is exactly the same, and growUp, except for, again, they're using this execute command. We've already discussed about the showResults, but let's come down and talk a little bit about this execute command here. So we're just passing in, this is called a parameter to a function, and this is the kind of thing that makes computer programs very, very different than sentences, because you can go in here and this same function will operate and do many, many, many different things based upon just the kind of data that you pass into it. So it will execute any particular command that's a valid command in DOS, or if you were running it on a Mac, that operating system. So whatever is valid for the operating system that you're running it on. So here what we're going to do is the same kind of thing that we've seen before. We're going to execute that command, except for instead of having a literal string that you can see, it's a variable. And we're going to wait. Now this is the main difference that we have between this and the previous functions in terms of waiting for that execution. We're only going to wait for 1 second. And so that's how you specify that right here. And then at the end, we're going to destroy. So now if the process has already executed or terminated properly, then this is fine. It won't bother anything. But if the process has not terminated within 1 second, then we will terminate it and we will destroy it. One other thing to point out here is this destroy function doesn't actually stop the program from compiling. It only comes into effect if the compile is not successful, because if it's successful, this will compile very quickly. And finally, if there are any errors that happen while we're executing, it will be printed out here. Then the very final thing that we have here is displaying the file, which we've kind of seen before. And all we're going to do is type out the cell type Java. So that is the cell that the child that we finally end up with. One other thing to point out, with just a subtle difference between this program and the other program. The other program, it'll work most times. There is a potential case where if the parent cell already existed, you might get into an issue. So what we have here is a copy instead of a rename. So that's just a little bit of a difference here, and we have that just like we did up here. So that's slightly different than the last program. Okay, now it's time for our experiments. If you remember, the way that we compile is Java-C and reproduceJavaMulti, and again have the Java extension so that we're compiling the program that is again equivalent to the biological machines that cause reproduction to happen. So now let's see what happens during reproduction. And again, we just type in Java instead of Java-C, reproduceJavaMulti again with no extension. It only made it one generation, or actually 0 generations, didn't make it the first one. And you can see that this is an insertion type of mutation, and it just is putting all kinds of gobbledygook in there. No real chance. So let's try again. 0 generations, again, just inserts a bunch of garbage. 0 generations, we're not getting anywhere close to 20 generations. So as you can see, oh, there we go. We get one that actually, no, it's really not useful at all. That's the point mutation. So this one you can see there's a number of point mutations. And as we can see, none of these things are actually increasing the information. They're not making it functionally superior. Okay, so we've come about to the end of this video, so let's take a couple of minutes to think about what we have learned. So first of all, DNA is operated on by biological machines, so computer programs are a very good way to understand what's happening in DNA. We can't rely on our subjective ideas of success to test our hypotheses. We need to test the functionality in a mechanistic way. That's why we measure the success by whether or not the child information is able to compile. The compiler is a machine operating on information, and that simulates what's happening when DNA is processed. Every attempt that we've made to mutate and compile is a scientific experiment supporting or negating the evolutionary hypothesis that natural processes can create functional information. While some mutations do not prevent the compiling, that is, the life, or the life of the child, no undirected mutations increase the functionality. Point mutations are insufficient to increase functionality, and the more mutations there are, the more likely it is that the child will not survive. Mutations are an enemy to functionality. So, in the next video, we'll show how variation can happen, not by mutations, but by design. I hope you enjoyed the video.